Okay, so welcome back, everyone. So in the first part, we have seen how to prove using the EasyCrypt proof assistant the security and correctness of an encryption scheme. And this encryption scheme was programmed in the imperative language that comes with the EasyCrypt prover. So I think you can see my screen here. And so this is the actual implementation of this encryption scheme as written in EasyCrypt. And it is written in a programming language, but this programming language is ideal in some sense. So the first thing is that it is not easy to run this program, or you cannot write an application that will call this EasyCrypt implementation for actually doing some encryption or decryption. So this is a first issue. And another one is that the language is such that a few low-level details are overlooked. There is no notion of runtime performance here. We don't know whether this program is slow or fast. And we don't know how these arguments and the return value of these functions are exchanged between the encryption scheme and the calling program. And another thing is that we have proved the security of this scheme in this ideal setting, but we did not consider that when we implement in an actual programming language that we run on an actual machine, an adversary may monitor some physical aspects of the execution, such as the execution time or the use of some shared resources like a memory cache. And by monitoring these low-level aspects of the execution, an adversary may learn some secrets through these so-called side channels. So in the second part, we will look at a programming language that is an actual language, such that you can run the programs in real applications and allow to reason about these aspects. So in theory, there are many programming languages that you could use and link with the EasyCrypt theorem prover in order to apply the proofs, such that the one we have done so far, to the implementations made in this language. But an aspect that is important usually when implementing cryptography is that we want the implementation to be extremely fast. And so we need a programming language that allows the programmer to have as much control as possible on the various low-level implementation details. So this is why we have designed the Jasmin programming language. So we want with this language to satisfy both goals. The first one is to make it possible to link the implementations written in the Jasmin language with theorem provers, such as EasyCrypt, in order to do security proofs. And the second aim is to give to the programmer all the control that it needs for making very efficient implementations. So briefly, what is Jasmin? So Jasmin is first a programming language, as I said, and we will soon see a few examples of Jasmin programs. And with the programming language comes a set of tools. And the first one is a tool that will translate a Jasmin program in an EasyCrypt model, so that we can do reasoning in EasyCrypt about the Jasmin language, the Jasmin program. And the second very important tool is a compiler that will take a Jasmin program and produce an assembly program corresponding to it. And this compiler is implemented and proved within the CogProf assistant. And by proved, I mean two things. In fact, there are two main theorems about the Jasmin compiler. The first one is compiler correctness, which means that whenever you have an execution of a Jasmin source program, then there is a corresponding execution of the assembly program. So in other words, the generated assembly behaves the same as the source program. And this compiler correctness result ensures that all the proofs that we do in EasyCrypt about the functional behavior of our Jasmin program also apply to the corresponding assembly program. So since we use a correct compiler, we are allowed to reason about the functional behavior of our program at the source level rather than at the assembly level. And the second important theorem about the Jasmin compiler is that it preserves particular notion of implementation security. And Benjamin will tell you more about this notion, but briefly, it's what we call constant time. So we have proved that if the source program is constant time, then the assembly program also is constant time. And constant time means that an adversary that can observe some side channels, like the execution time and the branches that are made by the program, and what are the addresses that the memory addresses that are accessed during the execution, then even if the adversary can look at all of this, then the adversary cannot learn the secrets that are manipulated by the program. And so we have proved that the compiler preserves constant time. And so again, this allows us to verify that a program is constant time at the source level rather at the assembly level. And all of these theorems, correctness, constant time preservation, and also the translation to EasyCrypt, have precondition that is the program safety. So before we can do any reasoning about the program, we have to ensure that it means something. And formally, we say that the the program has to be safe. And this is an undecidable property, but fortunately, there is an automatic checker that is able to prove program safety for most interesting programs. So let's look at a few example programs. So first of all, in the doc directory, next to the EasyCrypt cheat sheet, there is a Jasmin cheat sheet. So I won't go through it, but so this is a Jasmin programs that illustrates most of the syntactic constructs of the language. So I won't look at it, but please, if you need to read or write a Jasmin program, you can look at this file. And also, I wanted to mention that there is an online wiki. So here is the address. Okay, you can find it on GitHub, and here you will find a few documentation about how to use the different tools that will be presented in this lecture. So the Jasmin compiler that produces assembly, the safety checker that checks that the programs are safe, and the extraction of Jasmin programs to corresponding EasyCrypt models. So this was the EasyCrypt implementation of our encryption scheme. Now let's look at the Jasmin implementation of this encryption scheme. Here it is. So in the current implementation of Jasmin, we require that a complete Jasmin program fits in a single file. So we often use a preprocessor like CPP to manage modules and to split a program into several files. That being said, this is our Jasmin program. And in fact, we call it a program, but it's more like a library. So a program is a collection of functions. And here we have 3 functions defined. And the first one is labeled inline. And the 2 other ones are tagged export. And so those export functions are the one that actually belong to the library and that can be called from the outside. And the inline function here is just for the convenience of the programmer to be able to structure their codes and also to structure the proof. So this structure in functions is preserved during the extraction to EasyCrypt, but it's not preserved by the compiler. So if we look at the output of the compiler, that can be found, I guess, here. Yes. So we'll see that in the assembly that is generated by the compiler for this Jasmin program, there are only 2 functions, the dec one and then the enc one. And those functions are just straight line code without any other function call. So here, if we look at the source code of the enc function, we can see that it takes as input 3 values, k, n, and p, the key, the nonce, and the plain text. And each of these parameters is labeled with reg annotation, meaning that the parameter must be passed using the machine registers. And what this function does is first call the AES function that is defined in this AES lib using the key and the nonce to compute the text to compute the ciphertext, and this is returned as a result. And the dec function does the same. And so usually, so what you can see is that the parameters and the return type of this function are U128, which means this is a machine word of this bit width, and it is not always convenient when calling, when using other programming languages to directly manipulate values of this wide size. And so the Jasmin program, the Jasmin function, can also exchange data with the environment using the shared memory. And so we have another implementation of the same encryption scheme that uses a different calling convention. And so this is our different implementation. And the main difference is that the arguments have a different type, which is U64, and this is the size of the pointers. And so now there are 4 parameters and no return value, because this function will take as input 4 pointers, 3 of them pointing to some memory regions that hold respectively the secret key, the nonce, and the plain text. And the first parameter here is a pointer to a memory region to which the ciphertext must be written. And what this function does is to read the memory through these pointers, compute the AES as before, compute the XOR as before, and then write to memory the result. So this was just a brief illustration of what the Jasmin program looks like. And yes, the compiler from this kind of code that looks quite high level and structured will produce plain assembly. So one of the goals of this language is, even if the programmer has an assembly level control over the code that is generated by the compiler, well, the language itself does not look like assembly, and making it more readable both for the programmers and for the various tools that we use to formally verify these programs. So we have a compiler that from the Jasmin program produces an assembly program. And we can then compile, assemble the assembly program to machine code, and then use this machine code from other programming languages. So in the material, you will find examples of how to link with a Jasmin program from different programming languages. So from C, from OCaml, from Rust, and from Python. And we'll show you the Python example. So let me move to the Python directory. So in order to call the Jasmin program from Python, we have to make a shared library. So there is a makefile that can do that for you. And then we'll use the ctypes library in Python to load this library. So here is the first function that will do this loading. It's nothing special about Jasmin. And here is a real example in this round trip function. Takes as arguments, a pointer to our library, the secret key, and a plain text message. This function will sample knowns and allocate some memory to communicate with the Jasmin program, and then call the enc function from Jasmin. And then we call the dec function similarly and return the value after decryption. And here, this test case just chooses a message, a secret key, and call our run trip function and asserts that the original message is the same as the one after encryption and decryption. And what we have seen in the previous part of the lecture is that our encryption scheme is correct, meaning that there is no way to violate this assertion. And so I think I can run the Python program, and it prints the message before and after, and they are the same, so we are happy. It seems to work. So just let me do a small experiment. If instead of calling the decryption function with a pointer to some memory, I call it with a null pointer, I can run the Python program, and I get a very nice segmentation fault. So what happened? We have proved that our encryption scheme is correct, and we will prove by the end of this lecture that the Jasmin implementation that we have looked at is also correct implementation of this encryption scheme. And we have proved also that the compiler is correct, so it generates correct code. And so, however, we have here a failure at runtime. So, of course, this is expected because here I have given a null pointer to the Jasmin program, but I just wanted to recall that all of these theorems, the correctness of the extraction to EasyCrypt, meaning the correctness of the verification that we do in EasyCrypt, and the correctness of the compiler require that or only apply to safe executions. So what is a safe execution? It's an execution of the Jasmin program that has a well-defined semantics. And so this an execution to be safe has to satisfy the rules of the formal semantics. And so there are a few things. First, there are some arithmetic conditions. So you cannot divide by 0 or this kind of stuff. There are conditions related to memory accesses. So as in this example, the Jasmin program must only read and write memory at addresses that are properly allocated and properly aligned. Also, the Jasmin program to be safe must terminate, and this is quite unusual, but because we are focused on cryptography libraries, it's usually not an issue. All encryption functions terminate. And finally, yes, Jasmin programs may manipulate arrays, and array accesses must be in bounds. So those are the four main things that we need to ensure to make to claim that an execution is safe. And all of these rules might be a bit difficult to check, but fortunately, the Jasmin compiler can automatically check the safety of Jasmin programs. So let me try to do it now. So the Jasmin programs is this guy, and I can run Jasmin C with the check safety, and it says parse error. Oh yes, of course. Why does it say parse error? It's because I have this pre-processor directive, and the compiler doesn't know about it. So I have to look in the pre-process file, which is somewhere else. Okay. NBAS.jap pre-process. Okay. So what happens here when called with check safety? The checker says, I'm analyzing the function X and I found no safety violation. So this means that the function enc is safe. Well, we have seen that this is not true. So let's look at the rest. It says it is safe provided the arguments of the function. Okay, excuse me. Let's try again. This is not the file I want to check. This is the one. Okay. So this is the implementation that uses the that exchange the arguments and the return value through the memory. And so it says that the function enc is safe. There are no safety violation provided that the given arguments satisfy this condition. And here this condition says that all of them must point to valid regions of size 16 bytes. And then there is something that is irrelevant here. And finally, there is a last constraint about the alignment, saying that all of these pointers must be correctly aligned for accesses of 128 bits. So now let's look at the Jasmin language in some more details. So this is the basic implementation of our encryption scheme, and it relies on this AES library. So let's go and look at the AES lib. So this file defines a few functions, and mainly the AES and the inf AES functions. So AES takes as arguments the secret key and the block to encrypt, and will compute AES following the specification. And so if you are not familiar with AES, AES is a permutation that combines the secret key and the message to encrypt in several rounds. So there is some operation that is repeated here 10 times, and so each operation is called a round, and each round uses a secret key, and so there are 11 round keys. So there are 10 rounds and 11 round keys. And these round keys are not fixed. They are derived from the secret key that is given as argument of the AES function here. So in the first part of the computation of AES, these 11 round keys are computed by this keys expand function. And then we use these round keys to actually perform the rounds and compute the ciphertext. And in case we need to encrypt more than one block, we can compute the round keys once and then use them for all the blocks. So now we can have a look at the key expand function here. So this function takes as input the secret key and returns the 11 round keys. And these 11 round keys are declared here as a local variable as an array of 11 values, and each element of this array is a 128-bit machine word. And what is slightly unusual is that this variable is annotated here with reg, meaning that when this program is compiled to assembly, we want the 11 elements of this array to be allocated to registers. So if we had to write this in assembly, we have to pick one register for each element. And here we just ask the compiler, okay, we have a collection of 11 variables. We call the collection R keys, and we don't care what is the specific register that is allocated to each of these elements, but instead we just give to this collection a single name to make it clearer and more convenient. And then this function has a repetitive construction here that will compute each of the keys, each of these elements in the array. And so for this, we use a for loop. And in Jasmin, there are two kinds of loops. The one that are that use the for keyword, and the ones that use the while keyword. And the main difference is that the for loops, as they appear in Jasmin programs, will be completely unrolled during the compilation. So in the source, we have a loop, and in the assembly that is generated, this loop will disappear. And this loop uses an index round whose type is inline int. And inline int is the type of the computations that appear, that are evaluated at compile time. So we know that this round value here that is used, for instance, to index this array will be computed at compile time, so that the compiler will know precisely what are the elements of the array that are accessed. And maybe we can quickly look at the assembly that is generated for this program. And so, as I said before, even though the AES function at the source level calls the key expand function and then calls the AES rounds function, there is no function here. And even though there is a loop, there is no loop in the assembly program. But despite this difference, with a bit of experience with programming in Jasmin, it becomes possible to understand and even to predict what assembly is generated corresponding to a Jasmin program. So there is a very close connection to each instruction that appears in the Jasmin program and each instruction that appears in the assembly program. So this is one of the design principles of the language and the compiler, that what the compiler does is not surprising. The programmer is usually able to predict what assembly will be generated for a particular Jasmin program. So here, for instance, at the beginning of the key expansions, there are these 11 iteration of this loop that calls the key expand, which is defined above, and key expand is just a call to the AES keygen assist instruction. So this here, it's not a function call. This sharp sign here means that the program directly uses the machine instruction whose name is given there. So this instruction here is precisely found at the assembly level. without modification. And then there is this key combine, and key combine is doing some stuff with the contents of the registers. So it's doing some permutation, some XOR, some shuffling. And so we find all of these here. And then because we are within this for loop here, we will find the same pattern repeated 11 times in the target code. And a last word before I let Benjamin tell you how to do some proofs with this. So because we care about efficiency, we want to put all the data we manipulate as much as possible in hardware registers. But sometimes this is not possible. We'll have to move some data out of the registers and to store it into memory. And so as I presented before, it might be useful to exchange values with the environment, but also Jasmin functions can allocate some of their local variables on the local stack. And for instance, in this inv AES rounds, which performs the inverse AVS given the 11 round keys and the block to decrypt. In this function, for the sake of illustration, we have decided to put one of the round keys, the one that is used first, on the local stack. And so as we declare a variable, we can annotate it with stack, meaning that it won't be stored in a register, but instead it will be stored in the local stack of this function. And then when we use this variable rk in the add round key function, we use it as a regular variable, but it is annotated stack. So it means that here, when we access this rk variable, in fact, this is a memory access. And the same as we can declare an array and label it reg, like here, we have an array of registers. We can label an array declaration with stack, meaning that the array elements will be allocated to the stack. And therefore, whenever we access an element of the array, will in fact access the memory. And so if we briefly look at the inv AES function in assembly, we'll see the computation of the round keys. And at the end, the rounds, the 11 rounds. And the first round here calls the add round key before the first AES deck. And before the first AES deck, we see here the code for the add round key. And if you are familiar with assembly, you will recognize that this is a memory access to the top of the stack. So we have asked for memory access here, and we get here a store and a load of the first round key. So I think this ends my brief overview of the Jasmin programming language. there are many more things to learn about Jasmin, I think, but I will just hand the mic to Benjamin now.
Thank you. So I need to share my screen. Okay. Did you see it?
Yes, it's a bit small.
Okay. I don't know how to make it bigger, but maybe I will share after. Is it okay like that?
Oh, yes.
Yeah. Okay, so what we have seen in the first lecture is that we can use EasyCrypt to describe our cryptographic scheme, but this has been done really at the algorithmic level, relatively and completely abstract level. Okay, and once we have such a description, we can prove that the cryptographic correctness of the cryptographic security. And what Vincent just has present is that we can use Jasmin to write an efficient implementation of our scheme. So here in the implementation, we use some vectorized instruction to make it more efficient. And we have the fact that the compiler correctness will ensure that the assembly which is inherited is behave exactly the same as the source program. Okay, but in a sense, it's not very satisfying because we have a proof in EasyCrypt that the scheme is correct, but at the algorithmic level, and then we have a concrete implementation, but we don't have a proof that our concrete implementation is also correct. So the question is, can we have a proof directly that our code is functionally correct and also of the cryptographic security of our concrete implementation? So the answer naturally is yes, here at least. And the point is that the semantic of EasyCrypt program and of Jasmin program are very close. And this was an important choice in the design of the language, of the Jasmin language, to make it really suitable for program verification. And so you can extract using the command which is here, this stuff. So you call the Jasmin compiler, but instead of requiring to generate an assembly file, you require it to generate an EC file here. This minus EC, then you have to provide its argument. You have to provide the name of the Jasmin function that you want to extract, and here, and then you provide the name of the file that you want to of your source Jasmin program. Okay, so let's try first to do a small demo and see what's happened. So, is it still readable, or you need bigger font?
bigger would be better, I think.
Okay.
That's a lot better.
Thank you.
Just so we resize it. You can just do that. Okay, so here we have our Jasmin program, which just perform a code to the iOS, for example, here, and then XOR, and here in the EasyCrypt side. In fact, it's the same. So it's you do a function call to the IS procedure, and then you call the XOR function to mask and write all the stuff. Okay. And if we look again at for the encryption. So it was the code shown by Vincent. The structure again is very similar. So if we take, for example, the key expansion, we have a loop. So can I find the key expansion? And so here it's a for loop, and in EasyCrypt it will be translated into a while loop, okay, which at each turn will increment the counter by 1, okay. And so then you can remark some stuff. So here the key expansion expect say some data by 128 bits, and now here we use a special type which has been defined in EasyCrypt, which corresponds to word of size 128 bits. And here we say that we return an array of size 11, and here it says that the result will be an array 11, which is a special type for array of 11 elements, where each element are 128 bits, a word of 128 bits. Okay, and as you can see, the structure of both programs are very close, and so the translation from Jasmin to EasyCrypt is not formally proved. But the good point is, if you look at the semantic of both language, it's relatively easy to be convinced that the translation is correct. And this is true under the assumption that your Jasmin program is safe. Okay, else it's not correct. Okay, so now let's try to see what we can do with that. So let's see how we can prove that our implementation is correct and secure. So the idea is we will first instantiate the generic proof presented by François. But we will now say concretize all the type. So we'll say again, we say that the type of key will be this type, plain text is the same, nonce is the same. And since now we have a concrete type, we can also define the distribution of our key and the distribution over the ciphertext, which was necessary to define the scheme and the security proof. And we can say that it's a uniform distribution over a word of size 128 bits. And so we will take the theory presented by François and clone it by saying that its type for key is this one, type for nodes again is this one, and so on. Okay, and we have assumed that we have an operator f, which was our pseudo-random function. Okay, and we will instantiate this operator by the iOS operator. And the iOS operator is really a mathematical description. It's not the algorithm itself. It's, I mean, it's not the program that computes the iOS. It's really just its mathematical description. So it's, here, it's you can view it as a mathematical function. And also for the XOR, we can say that it corresponds to the XOR. And the leakage, we don't care. And then inside this this theory, we have some axioms that say, for example, that the distribution of size vertex is lossless. And since now everything is concrete, we can prove all those axioms. All this part is a proof that the axioms that we have assumed to do this proof are satisfied by our implementation. Okay, so after this clone, we can, sorry, this is wonderful. Okay, so let me cheat. This is a demo effect. I don't know what's happened, but let me admit it. I think, I don't know why it does not work. So let me 1 second. I should not focus on that. Sorry. Okay, so what we can do is to just print the scheme, and you see it's exactly the scheme present by François, but where the F operator here has been replaced by the iOS operator. If the security lemma, again is yes, it's just what you expect, where all the definition has been replaced. Okay. So, as Vincent explained, when we use extraction, or when you compile Jasmin program, you need to have the full program. So this is a little bit boring when you try to build a library, because here is a typical example. We have extracted from one side just the iOS part of our program, and then when we extract our scheme from here, we also have an iOS function. But these two functions, in a sense, come from the same program. So it will be completely trivial to prove that, in fact, they are the same. And for that, so we prove that if we start from two states where the arguments of the two programs are equal, then the result will be also equal. Okay, and you have the tactile sim that works, which is helpful for this kind of code. And on the library on iOS, we have already proved the correctness of the implementation. Okay, and this is more or less what we prove here for this program. which is, so if you start from, if you pass as argument to this procedure, a key and a nonce, then you know that the result returned by the procedure will be equal to the AES operator applied to the key and the noise. And so here, since we know that these two programs are equivalent, and we have from this lemma here, no, sorry, from this lemma, that it satisfies exactly this specification. What we obtain is that this program satisfies the same specification. Okay, so this is not really important here. We just to explain the small workaround that we have to do. So now our goal is to use this lemma to show that our program that we have obtained from the Jasmin implementation, okay, is equivalent to the scheme presented by François, where the function f is the AES operator. Okay, and so the proof is relatively trivial. Again, you do proc. So in this, in the left program, we call a procedure, which is our AES implementation, our implementation of the AES. Okay. And in this side, you see that it's not a procedure call, it's just an assignment from an expression. So it's this operator applied to these two arguments. And again, here we call a procedure, and here we do a simple assignment. So what I can do is just inline first the XOR operator, and we see that this procedure, in fact, just perform the XOR of the two elements. So we can use the WP tactic to consume all the basic assignment from this side and from this side. So this will consume everything from this side. And now I have nothing more, no more instruction on the right side, and I still have a function, a procedure call on the right, on the left side. Sorry. So we will use exactly this lemma that says that when I execute the AES procedure, I know that the result will satisfy some post condition. So I can do this equal stuff. Then I can do a skip. And I have to prove this formula, which looks ugly, but I can ask to simplify everything, and then everything is done. So it's why this by stuff is automatically. So we know that our concrete implementation is equivalent to the more abstract implementation that use an operator for the AES. Okay, so we can use again this lemma to derive the fact that when we I'm sorry, because in fact this lemma has not been present by François, but globally it's just express the functional property of our refining scheme for the encryption. It says that if we run, so here we prove that if we run the encryption that comes from Jasmin, then the result will correspond to the encryption of our plain text. Okay, we can do exactly the same for the decryption. And now we can use that to prove the correctness, the cryptographic correctness of our implementation. So what we do is we just instantiate, we define a concrete, what we call a concrete scheme. So we use the key generation, that just a sample key. But for the encryption and the decryption, it uses our concrete implementation. And so you can prove this correctness, but this I will skip that. I think it's not really the important part. The most interesting part is to show the concrete security. Okay, so we want to prove the CPA property of our concrete implementation. Okay, and we will show that we can reduce it to the PRF, to the PRF advantage of an adversary. Okay. So the first thing we do is we use we will rewrite the lemma proved by François, which will and we'll rewrite it in that direction. So it's allow me to replace this. So now what I have to prove is that this equality hold. So it's an absolute value of a difference, and the second part of the difference is the same. It's the ideal scheme, the CPA associated with the ideal scheme. And in this, for the first part of the difference, again, it is here, it's our concrete scheme. So this means our concrete implementation, where here it is just our more abstract scheme. Okay, so we will have just to prove that in fact these two terms here and here are equal. And to do that, it will be relatively simple because we know that the concrete scheme and the scheme are in fact more or less compute the same stuff. They are equivalent. Okay. So we use to prove this equality or probability, we use this bytecode stuff that allows us to switch to the PRF world. So we can do a proc. Against, we have a call to the adversary, but with different oracles. So we have to provide the invariants that allow us to show that the oracle behaves the same. And now I have to prove that the two oracles are the same. Okay, and you remember that in the oracle there is this wrap and the real scheme stuff. Okay, so we need to deal with that, but I'm not sure it's very visible. Yes. Globally the same if in both stuff, so we can use this kind of tactic. And again, the WP. And then the call, and now, which is an important point, is at some point I have to prove now that my concrete implementation is equivalent to the more abstract implementation, and this is the lemma on correct equips that we have proved already. Okay. So, which is important to remember here is that once you have proved the correctness, the security of your algorithm at in a relatively abstract way, and then if you prove that this abstract implementation is equivalent to your concrete implementation, so in a sense you have proved the functional correctness of your implementation, then it's relatively trivial to derive the proof, the security proof of your concrete implementation. Okay, do you have some question for the moment, or it's okay? Okay. So we have seen how we can prove that our Jasmin implementation is correct, and also cryptography. So it's cryptographic security. But the point is it sufficient? And so Vincent already explained it a little bit. But I think it's obvious that in general, it's not sufficient for crypto implementation, because the adversaries may observe more than just the result of the program. So in particular, when you run a program, it can measure the time the program takes to execute, or we can also observe the cache usage of your computer. Okay, so this will allow him to have to recover some information, and maybe those information will allow him to recover some of your secret data. So for crypto implementation, it is really important to be what we call cryptographic constant time. So informally, it's a kind of programming discipline where you never branch on secret data, because when you do a branching, you consider that the value of the test on which you branch will be leaked to the adversary. And also for when you do memory access, you should, the memory access, I mean the pointer itself, should not depend on secret. Okay, so if this means that if you read at address P, the value of P will be leaked. This corresponds to cache attack. And because for array, they will be compiled at the end to memory access, and for stack array in Jasmin. So this means that the value of the index will be also leaked. Okay. So more formally, when when we say that the program is cryptographic constant time, in fact, it's a relational property between two execution of the same program. Okay, and to define it, you need to first instrument your semantic, such that each time you execute an instruction, they will generate some leakage, and you will accumulate the leakage during the full execution of your program. So this is the L here. So when you execute a program, you start from a state S, you will go to a state S prime, and this execution will generate some leakage, which is in L. And to prove that the program is constant time, you will consider now two executions. So you start from a state either S1 or a state S2. You run the program, and it will generate, in the first case, a leakage L1 and a leakage L2. And what you want is to prove that the leakage, which is generated by the two programs, will be equal in both executions. Okay, so, but this is not for arbitrary execution. It should hold only for state which satisfies a condition field. Okay. And so, what is this condition? Morally, you can understand it as the two states are equal on the public part, and all the data which are secret can be completely different. Okay, so when we want to prove that, we have to verify that the program is constant time. We have two difficulties. And the first is that when you deal with program logic, generally you don't have this notion of leakage. But this is not really problematic, because the leakage can be easily encoded into a special variable. So as I say, when you execute an if, you will leak the value of B. So here the idea is to accumulate in a program variable everything which is leaked. Okay, so you will generate a model for this program where each time you do a conditional, you will first store the value of the test inside. You will accumulate it into a variable leakage, and then you perform your if, and you continue the execution. And inside the two branches, you will also add this kind of instrumentation. And you do the same when you, if you read from memory, then you will say, okay, the value of the pointer is leaked, so it will also set this value into memory, into the leakage variable. So maybe for those that are not used to this notation, this is the cons. So it's this means that the leakage is the previous value of the leakage, where we have added the value B at the beginning. So leakage itself is it's a list of values. The second point is that the usual programming logic are generally not relational, but maybe you have seen a little bit, but in EasyCrypt, we have this relational OR logic, so which allow to relate the two execution of two different programs. So we can use that, and in particular, sorry, I think I have not, I forgot to update my slide. but I will explain it during the demo. I don't know what. Okay, I forgot to update my slide, but not a big deal. Okay, so you can extract the implementation. You can generate using again Jasmin a concrete model. So maybe we can take a look, a model for constant time. So maybe we can take a look to it. Yes, here. So this is how look the extracted program when you require to generate a leakage, a model for constant time. And before, the tradition was, I mean, if you were looking the Jasmin program and the EasyCrypt program, it was almost one by one. And here you can see a lot of intermediate stuff which are a little bit dirty to read. But it's not really important because you will not really need to read it. But just to illustrate, here in the program we do an array access, and you see that the value of the indices is leak. And then in the original program it was a for loop, and the bound of the loop is also leak, and so on. Okay. And if we look for the same file, but the implementation that expect all the arguments from memory, so it's not a good one. This one, we go at the end. So the important point is that we read the value of the key from memory, so it's this instruction, and the value of the pointer, which is here, will be leaked, so set into this leakage function. So now if we want to prove that the function is constant time, it's here. What should we do? So what we want is to say that, okay, sorry, one sec. I have to tell to Inria that I'm still in live. Okay, sorry, it's because it's a night and I should not be at work. Okay, so we will look at two executions of the same program. Okay, and what we want is to prove that the value of the leakage at the end is the same. Okay, and because we accumulate all leakage in this variable leakage, we just require that initially the property hold before the execution. Okay. So we can do that. And the proof again will be very simple. So here you can just mark that normally it's a relational property, so we should have two programs, but due to the fact that it's one program with itself, so it's, we will not EasyCrypt don't print twice the program once. So we can inline everything, and we got a huge amount of instruction, which was horrible. But we have a dedicated tactic in EasyCrypt that allow you precisely to solve this kind of goal, where we want to prove a program which should be equivalent with another program where the control flow is almost the same, and your post condition is just equality over some variable. So, and this tactic is based mostly on variable on data dependencies. So it's completely trivial, in fact, to prove, but it's not surprising because our implementation here has been designed to be constant time, and this implementation does not use memory access. But what we can do is open the same file for the programs that use memory. So here, the proof will work almost in the same way, but you can see that now we require that the for argument of the function, which is a pointer where we will store the ciphertext, a pointer to the plain text, a pointer to the nonce, and a pointer to the key, need to be equal. Okay. And this, it's important to understand that so we need it because we will do some access to all those pointers. So if they are not equal in both execution, clearly the leakage will be different. Okay, but which is important, I think, to remember here, it's what we require is that the value of the pointer. So this means the address that will be read or write will need to be equal. Okay, but it's not the content of the memory. Okay. So the value of the key itself don't need to be the same in both execution. The value of the key can be a secret data. And just to do something that I really like. So here I can start by using a condition which is not sufficient, and try to prove it. And as you can see, in fact, I still have to prove something that, assuming that the leakage is initially equal, then the leakage is equal, but also all this stuff are equal. Okay, so this is clearly not provable because if I don't know the equality of the stuff, there is no way that I will be able to do it. But the important point to notice is that this seems static. You can view it a little bit as a type system that say to ensure that your program is constant time, you will need to have all those values to be public. Okay, the value of the pointer itself need to be public. And then, as a programmer, so this has been fair, but then as a programmer, you need to be convinced that it's okay for you to have to consider all those data as public data. But you have a kind of automatic inference. Yes, I cannot do a QED because I have not finished. And the last thing I would like to show it's here. So on one side, we have the security proof of our concrete implementation. On the other side, we know that our concrete implementation is a constant time, but this looks like two separate results. So what we can do is to show that, in fact, we can merge these two results to have a much stronger result. So we consider a scheme where when we compute the encryption, what we do is first we reset the leakage stuff. Then we compute the AES implementation, our concrete implementation, but here you see we use a model with a constant time. So this means that all the leakage generated by this procedure will be accumulated in the leakage variable. And at the end, what we return to the adversary is the ciphertext, but also all the leakage which has been generated during the computation of the encryption. Okay. And because we have, so we not explain the proof, but because we have been able to prove that our program is constant time, and also because it's equivalent. So what we prove here, yes, we prove that the model for constant time is equivalent to the usual model for security. And so here the function return, this function also computes some leakage, but if you don't look at it, then just the value of the result itself will be the same. Okay, so this, while the two extraction, so the model for constant time and the model for security, for just functional correctness, the two extraction look relatively different, but you can trivially show that in fact they will compute the same final result. And so you can use all those results to show that you can reduce the advantage LCPA. So the A is for leakage. So it's a slightly different game where each time the adversary calls encryption, you get the resulting ciphertext, but also the leakage generated by the encryption. And on the ideal side, you will be able to simulate the leakage, but without any information about your secret data. Okay, and again, you can reduce this advantage to PRF advantage of a given adversary. Okay, and this is just a simple result that you can obtain by combining all the results which has been presented before. Did we have question? Let's see. Oh. Okay, so let's go try to conclude. Sorry. Okay, so what are the main takeaways from Jasmin? So I think the most important point to remember, it's a language that has been first designed to be able to write very to write high-speed code. Okay, the idea is you should be able to write a program as efficiently as if you wrote it directly in a kernel. In assembly. I'm a kernel programmer, so sorry for this lapsus. So we use it to implement some various cryptographic scheme like the curve, poly 1305, cha-cha-20, and also Kipchak, which is Kipchak is a new, now it's not really new, but it's a SHA-3 standard. And there is some current work for to implement some post-quantum algorithm like Kyber and dilithium, but this is not finished. But for all of that, we have some code which is really efficient, and I think it's at least for poly cha-cha, I'm more sure that we are much more efficient than or previously implemented implementation. And the good point is when you want to write Jasmin program, you don't need to have any knowledge on verification. Just you can view it as a language to help you to write an assembly program. But it's clear that you need some knowledge on assembly to write it, okay? Because I view it a little bit like as a macro language to write assembly. So it's important to understand assembly when you want to write Jasmin program. The safety of Jasmin program, this has been shown by Vincent, and can be checked mostly automatically. This is okay. And the downside that we have for the moment is that the only assembly that we generate is for x86 on 64-bit platform. Then you can also prove that Jasmin programs are correct under constant time. And to do that, you can use extraction to EasyCrypt. So when you want to prove correctness of your program, and functional correctness, you just use a standard OR logic. This is relatively simple, and for constant time, it is done mostly automatically. And the really good point also is that the Jasmin compiler has been formally proved in Coq. So this allows to lift the property we have at the source level to the assembly. Okay, so so there is the first proof we have is for correctness of the compiler. So this means that the semantic of the source is the same as the semantic of the assembly. Maybe we should say it in the opposite direction. But we also have a proof, and this is much more unusual for certified compilers, that it's preserved constant time. This means that you have the guarantee that if your source program is constant time, then the generated assembly program will be also constant time. And the last point is what we should retain for EasyCrypt, from EasyCrypt. So you can use EasyCrypt in various ways. And I think if you just want to be convinced that your paper definition, crypto paper definition makes sense, it can be very useful to use EasyCrypt for that. Okay, because it will allow you to just provide you a tool where you can just check that your definition type check and make some sense. You can also use it just to specify your game hope. So this means that you, in your proof, you know that you will go from this game to this game and so on. And you can route all this intermediate game into EasyCrypt and just again check that everything that check and you have not forgot done some stupid error. Okay. So this, once you have done that, you have not a proof, but it's already a good first step, like a sanity check of your paper. The part which is then more complicated to do is to do your proof formally, and so to really prove your step. And this is clearly not automatic. So we have some automatization, but it's mostly manual proof. And I think on all this, for all these results, what you really need is to have some multidisciplinary team. You need to have people that know how to implement in assembly. You need to have people that know crypto proof, and you need also to have people that know proof assistant. Okay, and all this is a little bit having only one person that know how to do everything. It's unlikely, so it's much more easy to obtain that by using different people. Okay. Just one thing that I have forgot to say, it's on this stuff on constant time. So I have said that it's mostly automatic, and this is true, but it's true once you get a program which is constant time. So typically for the iOS, if we consider an implementation based on table for the iOS, it can be very efficient, but because you will do a lot of read into memory, and those read will depend on your secret key. It will not be constant time, okay? And there is no chance that we can help you to prove that this will be constant time. Okay, so the automatization works, but just for programs that verify your property. That's it for me. So thank you for your attention. So I don't know if there is a question for me or for Vincent.
First of all, thanks a lot for giving this talk, and also for staying up that late so that you already get a question. What was it, if you're still robbing light?
Sorry.
You said Inria was asking if you're actually using light or...
No, in live.
If you're still alive.
Yeah, because I'm alone, so they want to be sure that I don't have a heart attack or something like that. And so they call me every hour to be sure.
Indeed, I would not have been allowed to stay at the university. They would have kicked me out at 11.
Yeah.
So thanks a lot for this. I don't see any questions right now. So I think that would be the point where we stop the recording.